Cool. So, Dylan, maybe could you start off and just introduce yourself then?
Yeah. So I'm Dylan Baxter, mechanical engineer by trade. Got my degree at the University of British Columbia in Vancouver. As I was going through it, I also wanted to get a minor in commerce because I was super interested in the business side of engineering as well. From Kamloops originally, and went to school in BC, and then came out here to Ontario for work. And this is obviously where I signed up for the EIT program, and then got my PEng, I think 2 years ago now. It might be 3 years ago now. I was super into renewable energy in school. I
Hmm.
took one course that was called the Visualizing Climate Change or something like that. Something very simple, but it kind of opened my eyes to like kind of where the world was going. So I really wanted to be in renewable energy. And in BC, that pretty much just means that you work for BC Hydro, and that's it. um, moving over to Ontario, there was a lot more opportunity for going into solar, or in my case, going into wind energy. So right now, I'm the director of technology on the Borealis Wind team at Fabric Air. Borealis Wind started off as a school project at UBC Vancouver with myself and right now who's the VP of Borealis Wind, and it was part of our capstone project at school. And then after we tried to turn it into a company, and we joined the Velocity Incubator here in Waterloo. And then from there, kind of built it up over a couple of years, doing technical validation and a few pilot studies, and then expanded our customer base. And pretty much what we make is a hot air system that goes inside the wind turbine blades to heat them up during the wintertime to prevent the amount of downtime that happens during the winter because of iced turbine blades. Um, so that was a lot of fun trying to engineer through going through design process, doing a lot of field work, a lot of measurements in person to really understand how our system can fit inside these existing wind turbines. Because we took a very unique approach to it right from when we were in school, we took a unique approach. We did a little bit of computational fluid dynamics modeling to really understand the airflow going on inside the blades. And then we landed on using flexible fabric ducting rather than traditional metal ductwork. And this really kind of set us apart. It opened up a whole new world that a bunch of other companies had tried to do over the last 20 years and failed because they were using traditional metal ductwork.
Skills or talents or tools do you need to bring to the table to do this kind of work?
Yeah, definitely. The engineering design process has been super important. The whole understanding that you have to gather your like needs and requirements and constraints, identify concepts, winnow those concepts out, create prototypes, do analysis on those prototypes, whether it's analytical prototypes or physical prototypes, and then always being ready to kind of cycle back at any stage of that design cycle if you hit any roadblock. So that whole process was really like hammered into us in at UBC
Yeah.
Vancouver. And it has pretty much guided how we approach all of these engineering problems, and even non-engineering problems as well. We still approach it with the same mindset. And we've just been able to get through whatever obstacle we've kind of hit just by following that exact same process. So that's definitely the most important skill.
This was sort of a startup, so pretty small to begin with.
Yeah, startup. The smallest we've ever been was 4 people when we first started. And then right now we have about a dozen on the Borealis Wind team specifically. But just 2 years ago, we were purchased by our fabric ducting supplier called Fabric Air. So now we're part of a larger family uh, of like people around the world. I don't know, a couple hundred, something like that.
You got installations all over.
Yeah, we've got the lowest hanging fruit is in Quebec. So the
Huh?
worst icing and the most wind capacity. So we've been mostly targeting them for the past couple of years, a little bit in Ontario as well, like Northern Ontario. We've had our eyes set on a few wind farms across Saskatchewan, Alberta, and BC. Fabric Air parent company is based out of Denmark. we're trying to push up into Sweden and Finland, where there's a lot of other low-hanging fruit as well.
Obviously, you've been up in a turbine.
Yeah. Oh, yeah. Got lots of hours up in a wind turbine. Lots of different wind turbines. They're like 100 meters up in the air, and so they're a pretty unique place to be working in because, especially, we go inside the blades, which is a small hollow space. So it's a confined space, but it's at heights. So you have confined space safety training and working at height safety training, and like you need to do a few yoga moves to get inside. And those are maybe like 5 feet tall in diameter at the largest spot. And then we've also been in blades that are more like 9 feet, maybe 10 feet tall in diameter. And where turbines just keep getting larger and larger every year, right? So we're looking at ones now that are more like 15 feet wide in diameter at the root. Most of these large turbines are produced out of Europe. A lot of the components are produced like in North America. So, for example, up in the Gaspé region in Quebec, there is a large blade manufacturing plant there. So if there's wind turbines that are being put up in Canada, most likely the blades came from that factory up in Quebec.
Do you ever find yourself dangling off a rope at several meters in the air, or some crazy thing happen while you're doing this?
Nothing too crazy like that. No dangling off ropes for sure. But there is one turbine type that we've been in. They're made by General Electric. They're made by GE. To get into the blade, you have to go up onto the roof of the generator, hook all yourself off so that you don't fall off, walk across the roof, drop down into the hub, which is the part that rotates, and then go sideways into the blade, which pitches and spins. So the whole part of going up onto the roof, walking across and dropping down was very nerve-wracking the first time I had to do it.
So you mentioned you've kind of transitioned through the EIT and pathway yourself only a few years ago. Are you working with other EITs or engineering interns on the project?
Yeah, so especially when we were in our startup phase, we would always have co-op students. We typically have a mechanical co-op student, an electrical co-op student, and a control system co-op student pretty much every semester. So these were people who we were working with, and also either they were signed up for the EIT program or we were trying to convince them to sign up for the EIT program as well.
So I wonder, just on the technical side, what kind of skill sets or programs, would you encourage mechanical engineers or engineers interested in this kind of thing? What should they be studying? What should they learn? What can they learn on the side to be prepared to get into wind energy?
One of the big ones is like a CAD software. So we use SolidWorks, and pretty much anytime we're doing any sort of design change, we have to have a point of truth, and that point of truth is typically captured in CAD. So all of our mechanical designers, they have to be very good at opening up an assembly, being able to filter down the family tree down to the single component that needs to be changed or analyzed, and then making that change, swapping it out, and making sure that nothing breaks all the way up to the top level assembly as well. One of the biggest one of the biggest problems that we always find is that everything that we buy is not meant for a rotating, vibrating environment, right? If you buy any electrical component, it's supposed to be mounted in one direction. If you buy a mechanical component, it has either a fatigue life or it's not rated for specific vibration resistance, that kind of stuff. So we have to not only shop around to find the best component, but we also need to do the testing or analysis in-house to see whether it can survive this rough environment of rotating, hot, cold, vibrating. So just understanding the physical environment that you're putting your design into is super important as well.
I come out of the aerospace bearing industry myself. the speeds, the temperatures, the change in speed, the change in temperature, the torque
The rate of
reversals.
change of speed, the rate of
Yeah.
change.
Right. Everything in dynamics is so much different than static systems. So,
Yeah. We try and do as much tabletop and in-shop testing as possible before it goes out to the field, but there really is no replacement for the in-field testing as far as wind turbines go. So we were able to create a one-to-one replica of a blade inside our test wall or inside our shop, and we call that our test wall. And so we install our blower, our heater, our duct. We create a see-through blade shape with very rudimentary measurement tools. We would dangle yarn inside to be able to visualize the
okay.
flow. Very old school, like what was done
Right.
a long time ago for airfoils. So we would do that to be able to observe the airflow, and we take measurements, all of our pressure, temperature, air velocity measurements everywhere, wherever we can. So we try and understand everything that we possibly can about the system on the floor, make sure that all of our calculations check out. We'll see where we need to adjust, maybe where our assumptions went wrong, tweak those physical parameters, and then send it out to site. And for the first year that a new design is installed, we're monitoring it constantly. So we have to make sure that it's performing the way that we expect it to. And as soon as it starts deviating from that expectation, then we go and do those site visits to see what was really going on.
Cool. So then maybe I'll finish by looking ahead. Do you see any new technology that you're starting to use or that you're looking at for future use that sort of changes this industry or changes this sort of system?
Yeah, for sure. And you'll probably get the same answer from everyone who you ask, but AI obviously right now is the
I was
hugest
I was thinking
disruptor.
about it and I thought I know a little bit about artificial intelligence and different systems, but I can't think of how you apply it here.
How we
So
could get it
I'd
in
love
there.
to
Yeah.
hear.
Yeah. So we've gone from spending 90% of our engineering hours on mechanical and electrical design to maybe 10 to 15% of our engineering hours on mechanical and electrical. The other, whatever, 90, 80% is now on how we can close that engineering feedback loop, because we've gone all the way around to deploy and then we want to be able to come back to see if there's any improvements. So we're closing that engineering feedback loop by collecting large amounts of data on our system. We're collecting 1 second data on temperature, pressure, positioning sensors, contactor statuses. We're collecting all of that. Turbine performance as well. So how our system is actually affecting the turbine performance. So we collect all of that, and now we have 5 years of data in this huge database. And now we're trying to make dashboards out of it. We're trying to understand what the difference was between turbine A that was successfully de-iced and turbine B, which was literally right beside it, didn't successfully de-ice on that day. What was the difference there, and how can we capture it so that one turbine, or so that both of them are successfully de-icing? So we're using AI a lot right now to help build out these tools. So something that would take a team of 4 or 5 people a few years ago, now we can sit here with a few well-described prompts, and we can use ChatGPT to essentially create those tools for us, and we can visualize the data properly. We can ask it to manipulate the data so that we can do what-if scenarios.
So I read a study that talked about using IoT devices in wind turbines to develop a predictive failure model.
Yeah, for sure. So what we're doing right now is looking back on the previous data, and what we want to do in the next year or 2 years is to extrapolate that forward. So exactly what you're saying, preventative maintenance. For example, if our pressure sensors are slowly declining over 2 years, does that mean that our blower bearings need to be replaced, right? So can we predict that? Can we be monitoring that over a 3-year period? And then AI is going to be telling us, hey, you should probably plan on replacing this blower, not this year, but next year, schedule it. So preventative maintenance, and then smart triggering. So we have found that it's super important to turn on the heating system at the right time. Too early means you're wasting energy. Too late means that the ice is already accumulated and now it's harder to get rid of. Keeping it on too long after the icing event is wasting energy. Turning it off too fast might mean that not all of it was shed, right? So there's a lot of triggering knowledge that we think is baked into all this data we've collected, but we want to use models to try and pull that out to be able to synthesize it, to put that back into our control algorithms that we can precisely trigger at the right time. And even we want to be able to use other predictive models that other people have already published, like weather predictive models and even power price predictive models, to try and fine tune that to say, yeah, we could probably de-ice in the next hour, but the price of energy is skyrocketed right now. So we don't want to turn on the heaters. We'll wait until it goes down and then we'll turn on the heaters. So it's super exciting, like all the kind of stuff that like we have as an opportunity with this massive amount of data sitting in our office.
That's fantastic.
Yeah.
I appreciate you sharing all this with us. That's beautiful.
No problem. Take care, Brad.